The next speaker is very important and a dear friend of mine, Lars Brink. Lars is a world-renowned particle theorist, elementary particle theorist, and he is also very important in the Swedish physics community, as we all know, where Swedish physics is important to every single one, especially in the coming 2 weeks when the next Nobel Prize will be announced. Lars, the screen is yours.
Thank you very much. Let me just see if I can get my screen. So you cannot start screen share while the other participants are sharing.
It's on. Okay.
Is it over? Can I do it now?
Hello.
Oh, yes.
Here it is.
And I also just have to make it big. Sorry, I will.
Got it.
Why is it not working?
Well, it's very clear, so let's go on.
Okay, let's go for that. So thank you very much for inviting me to talk here. It's a great pleasure, and it's also very interesting for us on this side of the Atlantic to be part of it. So what I will do in this talk is that I will not talk so much about her life. I will talk about, as I say, 2 gems in a box of pearls, 2 experiments that were, I can say, of Nobel class. And it's interesting because one of them was not mentioned in the first talk of today. So perhaps even the Chinese Physical Society can learn something. Oh, I'm sorry, I have to do it differently here. So anyhow, after the World War II, there was a generation of brilliant physicists coming together after the war. And you know, it was many people had been educated at Los Alamos and the Red Lab, and the war had attracted the most sharp young students of the time. So they came back together with the previous generations that had also been, you know, excellent. And the question is, what should they work on now? As the young, precocious student Murray Gell-Mann later remembered of this time, was that theoreticians were in disgrace. So yeah, what should they work on? Should they work on nuclear physics? Okay, look at that. Madame Wu was constantly working, you know, in this field, and she was doing brilliantly. So that was okay. But elementary particles, well, that had not really started, you know, to be a major field because there were no new data yet. So among these theorists, John Wheeler had an idea, which was very interesting. He said that there is just one electron in the world. And if you draw it, you know, in time, and you take a time slice, then you will see when it comes up, it's a electron. When it goes down, it's a positron. So you can, by this, you will get both electrons and positrons. But the thing is that they are connected. They're really part of the same electron line. Of course, this was the wrong idea, since there are more electrons than positrons. But it showed, you know, that electrons and positrons in a decay are correlated. So Wheeler proposed, well, I should say that he called his former student, Richard Feynman, and Feynman got very excited, and he worked out the consequences of it. And what the consequence it was that Wheeler could propose an experiment to verify what they call the prediction of pair theory, that two quanta emitted in the annihilation of a positron-electron pair with zero relative angular momentum are polarized at right angles to each other. And note that this is a macroscopic effect. Quantum mechanics had been used, sort of linearly, and we had not seen any real macroscopic effect of quantum mechanics. This was the first example of a macroscopic effect, that particles at a macroscopic distance away somehow knew of each other, that they were correlated. If we did something on the one, it was affecting the other. It was a completely new physical phenomena that people had not really thought about before. But then in June 1947, at Shelter Island came the big avalanche of new ideas, because that was the lamp shift, also coming from Colombia. Rutherford and Lamb had discovered that there is an inherent shift in the electronic levels, atomic levels, which is inherent in the sense that it's not affected by external particles. It's really a quantum effect inside quantum electrodynamics. And now theoreticians got busy, and you've all heard about the history about this, and QED was invented. So somehow Madame Wu's, or not Madame, but John Wheeler's idea were sort of buried, that was put aside, because all the theoreticians were busy with QED, and experimentalists could continue Lamb's work. However, in 1949, scintillation counters had been developed, and Madame Wu could now check Wheeler's assumption. So they had developed a positron source, copper 64, and it was activated by deuterium bombardments on a copper target in the Columbia cyclotron. So in taking the coincidence measurements that we were looking at, one detector was kept fixed in position, and the second detector was oriented to 4 different positions with azimuth difference 0, 90 degrees, 180 degrees, or 270 degrees between the detector axes. After that, the second detector was kept fixed, and the first one rotated. So the total period of measurement lasted about 30 continuous hours.
Wow.
Here you can see the devotion of Madame Wu to an experiment. So they were really doing experiment 30 continuous hours.
Wow.
And the result was wonderful. So they measured the asymmetry. And from the best round is that the coincidence rate counting rate for when the beam is perpendicular to the coincidence rate when the counting rate is parallel was 2.24 plus minus 0.8. And the calculated asymmetry for her geometric arrangement was 2.00. So her measurement was extraordinary. It was well within the errors, and it was clean. This was an experiment with Shaknov. And so it was really clean. It was the first test of macroscopic entanglement. Was it Nobel Prize height? In retrospect, I would say that, absolutely. She was, it was a really major new insight into quantum mechanics, namely that you have correlations over macroscopic distances. So it was macroscopic entanglement. Was it, how was the reaction? Well, people were so busy with other things, so they did not really take much notice. So again, this is one of these discoveries which is discovered far too early. So let's come to the next gem, which we know more about. In 1949, Einstein was 70, and Paul Dirac wrote a famous contribution to the memorial volume called Hamiltonians, in which he went through Hamiltonian dynamics, also for gauge theories. And this paper was very important for much later developments. It came back, to people's attention in the 1970s. But it was one of these papers where Paul Dirac, he could make statements which he didn't really need to prove. So he said that he did not see any reason why parity should be conserved. But he says people seem to be convinced of it. So he sort of shrugged his shoulders, and not much more was discussed from that. But then when particle experiments started to produce new processes in the first half of the 50s, it was found that there were two particles with the same mass called theta and tau. But the funny thing is that tau plus decayed into 3 pi plus or 2 pi plus and 1 pi minus, and theta plus into pi plus plus pi 0. But it had been established that pi had a parity of actually it could distinguish between left and right. So if you check, if you believe in parity non-violation, you see that theta plus was okay, but tau plus was not, because if it looked as if it should have parity +1. So something was wrong. And it had to do with parity. I'm sorry. And among the leading theorists of the time, T.D. Lee, Xian Yang, Murray Gell-Mann, Richard Feynman, they discussed, if this could be parity doubling or parity violation. But they didn't. It's remarkable going back to the history to see that Murray Gell-Mann was certainly discussing parity violation, and he got a lot of opposition to it, but he didn't do the check. I don't understand that. And the one to really check the case was Lee and Yang. And they found that they lacked proofs that parity is conserved. And they went through several ways to check it. And here comes the interesting thing with Madame Wu. So they first proposed to test it in the beta decay of cobalt-60. And this shows very well that this was, very much discussed with Madame Wu, because she knew, how to line up atoms in a magnetic field, and she was a world expert on beta decay. So she knew that this was an experiment she could do. It's a difficult experiment, as you know, but it could be done. Actually, had they discussed it with another younger theorist, experimentalist at Columbia, Leon Lederman, he would have said that you should check it in particle scattering. You could really measure it in particle scattering. But they thanked Madame Wu for the discussion, and not Lederman, although he was also in the lab. So you might say that they overkilled. On the other hand, there was also a remarkable experiment once you know that it showed parity violation, because it was easy to describe it to students, to other physicists. And it was clear from the beginning that this was a good experiment. So she performed, as we have heard, the experiment at the National Bureau in Washington with Ambler. He was the one who could provide the low temperature laboratory. And it was technically very demanding experiment. And on January 15, they submitted the result. Parity was broken maximally. Lederman submitted his result the same day, but insisted to be placed after Madame Wu's article. There was also a paper by Telegdi and Freeman, and with the same result, but that was published in the volume after, the week after, which they were rather unhappy about. So there was a really, a fantastic new result, and it was very much discussed, and it changed, the development in particle physics, in fundamental physics. And already in 1957, Xian Yang and T.D. Lee got the Nobel Prize in Physics for their penetrating investigation of the so-called parity laws, which has led to important discoveries regarding the elementary particles. And I was a schoolboy at the time, and when they came, for the Nobel ceremony, people were extremely excited. They looked like schoolboys to Sweden, to the Swedes, and they became very popular. And it was one of the most, discussed prizes. One of it was fantastically good for physics, because it showed, that there were, in basic science, there are laws which are different from what we can think of. We really have to follow elementary particles and follow what's happening at that level. However, there is one question. Where was Madame Wu? She had discovered the parity violation. And, it's 70 years ago, and we can still not check the archive, because both Li and Yang are still alive. And we can only wait for the archives to open. We should not wait for it, because we would like them to live as long as possible. But it's clear, that the whole process was too quick. The nomination was in the last of December. The decision was taken in October. And they had not, we can see now in retrospect, they had not gone through the full procedure as it should have done. I can only give you one clue, and that was that which you can, in principle, find on the net, that the Nobel Committee was then dominated by two world-leading theorists, Oskar Klein and Ivar Waller. So she didn't get it. Some years ago, I had a dinner with Xian Yang in Singapore. He asked me, why did you not include Madame Wu in the prize? I answered, I was a schoolboy at the time, I had no influence. Should the committee have included her? Yes, he said, emphatically. And I could not agree with it more. So thank you.
The last slide tells all, Lars. Two things in your talk. First, of course, the last slide. The second thing, I think your talk is probably the only one in our entire talk, all the talks today, where the word entanglement shows up. And,
Yes.
We're so blinded by the fantastic experiment of parity non-conservation that sometimes we forgot that she had other great discoveries. And entanglement, which is 70 years later now, a hot subject in quantum computing and quantum information, where she was a true leader. Thank you so very, very much for pointing this out today. Thank you. I think it really made our event today historical. Thank you.
No, thank you. Yeah.
The next one is a very important participant as well, is Professor Wang Yifang, the director of the Institute of High Energy Physics in the Chinese Academy of Science. An important thing, besides being a great physicist, Wang Yifang, just like C.S. Wu, was also trained as an undergraduate at Nanjing University. Professor Wang.
Hello, can you hear me?
Very well.
Yes, let me share my screen. So first of all, it's a great honor for me to be able to speak at this very important historical event. As Daxun just mentioned, I'm a alumni of the Nanjing University. It's really a great honor. And indeed, Madame Wu has been inspired us since very beginning as a physics undergraduate. So you all know that Madame Wu had experimentally discovered the parity violation. And this is her very famous paper published in the year of 1957. And indeed, her discovery led to the Nobel Prize of two other Chinese origin particle physicists, T.D. Li and Xian Yan. And indeed, Madame Wu made major contributions to the discovery, not only the experimentally, but also to the idea of the parity violation. As a world leader expert of beta decays, she actually told T.D. Li in May 1957 that all existing beta decay results have only measured the energy spectrum, not the spatial distribution of beta decays. So, which means that there's no proof of the parity violation in beta decays in the past. So she proposed the idea to use cobalt-60 beta decays to test the parity violation, and she did it, and she made this major discovery. Just a few months later, Li and Yang realized that the parity violation has a direct relationship with neutrinos, or in other words, the parity violation actually came from the neutrinos, because if neutrino has no right-hand components, it's going to violate completely the parity, and this result in the famous V minus A series of neutrinos, and afterwards it becomes a V minus A series for weak interactions. And indeed, we now know that the parity violation is really because of the neutrinos. So we all know that C.S. Wu is a world expert on the beta decays. So indeed, she later made experimental tests of the V minus A weak interactions through beta decays. So these are her experimental measurement with all the possible helicities, and she proved that indeed V minus A is the right description of weak interactions. She also tried to use beta decays to measure neutrino mass, and this is one of her major results on the measurement of the neutrino mass through beta decays. And you can see that this is in the year of 1980s, and currently we know that the M beta is now less than 0.8 eV from a Catherine experiment in Germany. And at that time, Madame Wu only measured to the level of roughly a few eV, a factor of roughly factor 10 higher. Madame Wu also worked on the neutrino double beta decays, trying to see if the neutrinos are Dirac or Majorana. So she worked on the calcium-48 and also worked on selenium 82 and other isotopes. And of course, so you can see that Madame Wu are the real expert on beta decays, double beta decays, and the neutrinos. So a few words about my personal career with Madame Wu. So in 1980, I became a student at Nanjing University with the major of nuclear physics. And this field in Nanjing University was established by Professor Shi Shiyuan. He just passed away in 2007 at the age of 100. He got the PhD degree in 1933 with Madame Curie. And indeed, when I was at the university, she came to us very often, and he came to us very often, and was very kind to us. In 1930, Madame Wu, just 50 years before I entered the university, Madame Wu was admitted to the National Central University. It's actually the predecessor of Nanjing University. And she completed her bachelor's thesis in 1934 under Professor Shi. So you can see that the two great women physicists of the last century actually are directly connected through the Professor Shi. And in 1982, Madame Wu actually visited Nanjing University and gave many talks. I still remember some of her suggestions. For example, she actually suggests us to read the famous book, First 3 Minutes, just came out at that time by Weinberg. And she suggests that the Nanjing University can work on neutrinos, and because neutrino experiment usually cost less compared to other particle physics experiments. So in 1996, actually, I started to work on Palo-Verde neutrino experiment, which was led by Professor Felix Byrne from Caltech. And he was actually a postdoc of Madame Wu in 1951. So Palo-Verde was the first neutrino experiment I worked on, and later on, I started to work on diabatic neutrino experiment in China and trying to look for a new oscillation mode called θ13. And the θ13 allowed region is depicted in this picture, and you can see that Palo-Verde experiment actually excluded this region, and combined with allowed region from super K, these are the allowed parameter space for the θ13. And indeed, in 2012, we managed to see sizable θ13 value, which is 0.092 with the 5.2 sigma for the non-zero θ13 values. So this was actually a major observation on the neutrino physics, and with the observation of θ13, now we have a complete picture of the neutrino oscillation, and we know that neutrino has a mass. After the diabatic experiment, we start to work on the next step, the so-called Juno neutrino experiment. And the science goal of this experiment is the neutrino mass ordering, the precision neutrino mixing parameters, supernova, solar, and the geoneutrinos, etc. And in particular, we'd like to upgrade this experiment in the later on the stage for double beta decay searches down to the mass of 10 milli eV. So this is almost kind of the word most sensible double beta decay experiment to have been designed up to today. And the Juno experiment is under construction. This picture shows you its current status. And in about a year from now, we are going to finish the construction and start the data taking. And the Juno collaboration is a very large international collaboration. We have 19 countries and the regions from 74 institutions with more than 700 members from all over the world, the Asia, the Europe, and also United States. But also in the United States, there's another neutrino experiment called the AirBeam F and Dune, And this is a long baseline accelerator experiment, neutrino experiment, which is under construction right now. And up to now, the civil construction is in good shape. Accelerator is under upgrading, and the data taking is planned for 2028. So this comes to my summary. Madame Wu and Madame Curie are the two greatest women physicists in the history, and they are marvelously connected by Professor Shi Shiyuan, who taught thousands of students in 70 years at Nanjing University, including my teachers and myself. Madame Wu is very influential in both the US and China, with many academic successors. And neutrino physics, which she pioneered, will have a great future. Hopefully, in 10 years, oscillation will be completely known. And in 20 years, the absolute mass will be known. And in 30 years, we may know that neutrinos are Dirac or Majorana. Let's collaborate for that. Thank you.
Thank you very much. This was such a remarkable account of Madame Wu's interest in all these fundamental areas of physics. You mentioned Shi Shiyuan. In 1983, when I first visited China, that is after 1949, after I first visited China, I was invited to the home of Chen Jingquan, Professor Chen Jingquan in Nanjing University, and the other person at dinner was Professor Shi Shiyuan. Little did I know that Shi Shiyuan is the bridge between the two great madams of physics of the 20th century. Thank you very much for pointing that out. This is such
Thank
a
you.
beautiful, beautiful story. I'm glad that we have an opportunity that finally we can tell the world that the two madams are actually connected in some incredible manner. Thank you.
Thank you.
The next we have is another leading leaders of the American Physical Society, the former president of APS, Sylvester James Gates. He's currently a faculty member at the University of Maryland, but he has so many accolades. One of them, of course, is the Presidential Science Award, and so on and so forth. So maybe I can just, to save time, you can look at his bio and ask him to launch into his talk, which I'm sure is going to be beautiful. Jim, are you there?
Yes.
Oh, okay.
Well, first of all, let me express my appreciation to all of the organizers of this marvelous meeting. And it's amazing to actually reflect on Madame Wu. I'd like to welcome all of our guests, all our honorable participants, and most of all, the audience that's out there listening to us all pay proper tribute and honor to this great, great physicist. I actually first heard about Madame Wu when I was a freshman at MIT in 1969. And there was news of this Asian woman who was out doing fantastic physics. And as a minority myself, that was encouraging for me. Because one thing that we've talked about a lot today is the role of Chinese Americans and their contributions to the development of physics. But one thing I've learned over the years is that whenever someone who is a minority steps up to the challenge that both nature and intellect present us in trying to understand how she works at the most intimate levels is that people will watch. And so she became a role model for me, as I have in my career experienced being a role model for young Asian scientists in Australia, which was a shock for me to learn. And so the message is that as physics opens up to everyone who can make a contribution, she will also open her doors to more people who can make the contribution that might be extraordinarily important. So I thank you for allowing me to be here, and especially to our organizer. I also have to say that this meeting is special to me because I had a chance to reconnect with a Chinese student who I taught quantum field theory to over 20 years ago. And that is the Honorable Liu Jing Lai, who spoke earlier. He was one of my students. And this is like the third or fourth time in my life that I have found that Chinese students that I taught in the 80s and 90s are now in China, principally, doing great work in physics. And so it adds to just pure joy, because you see, this is my 51st consecutive year teaching at the university level. And so to have students over generations coming back and saying, well, they don't say, thank you for not giving me an A, but they're very kind. So let me get started in my presentation as I pay my tribute to Dr. Liu. And I'm pulling up my copy on my machine so I don't have to keep constantly looking over my shoulder to deliver the presentation. So what I wanted to do was something slightly different. There's been much praise for Dr. Wu and the many, many contributions she made to science, to both countries, to multiple generations. And earlier today, my colleague, Young-Ki Kim, spoke about her. And so we decided to split the task. Young-Ki was going to talk about the broad breadth of Madame Wu's impact. And I was only going to confine my presentation to what I like to call the mandate observation. Maybe some people know what the expression mandate of heaven means. And so I'm drawing upon that meaning when I talk about the mandate observation. So next slide, please. We've heard much talk about today about the famous experiment where she looks at cobalt as it transitions under the effect of beta decay to nickel. And in the process produces electrons and actually anti-neutrinos. So I'm currently teaching a course called the Manhattan Project at Maryland. And one thing that I can tell you for people who are not scientists and who are not physicists is what the challenge is as we scientists try to speak about nuclear physics. And so the first thing I'm going to do, next slide, is to take you on a small journey. But the technology doesn't seem to be supporting it. This is actually an animation. And that's an animation. So I'm going to have to do this by hands, folks. Technology is failing me. So start from a meter stick, cut it into 10 equal pieces, throw away 9, keep 1. You go from something this big to about something that big. Do that process again. Animation's still not going. Do that process again. And you go from something this big to about the width of my fingernails. I often stand in, when I teach something about nuclear physics to non-physicists, I ask, how many times do you have to do that to get to the size of the atom? And unless you're a scientist, most people don't know the answer. And maybe even if you're a chemist, you might not know the answer. The answer is 10. That's how you get from our world to the size of the atom. And then you can ask the question, how many further times have to do this process to get to the size of the nucleus? And the answer is 5 more times. So that's where nuclear physics resides. It's 15 times this power of 10 argument. Next slide, please. Since my animations don't seem to be working. So in the nucleus, It turns out there are only three forces that are important. There is electromagnetism acting on the charged protons. There is the nuclear force, which actually glues the protons and neutrons together. Otherwise, the protons would be expelled. And then finally, there's the weak nuclear force. So those are the three forces that Madame Wu was exploring in the domain of her work. You might wonder about gravity, but it turns out in the realm of the nucleus, gravity is not that important. So her experiments, next slide, please. Oh my goodness, animation just started. And this one looks like it's not. Next slide, please. So in nuclear physics, we like to put things in big baskets. And this is a very famous curve because it explains a lot about our world. You see, as you go to the red side of this curve, what you're looking at is the ways that stars cook elements. We start with hydrogen, and then we bond it together to get to helium. And it turns out helium is more stable than hydrogen. That's why the sun converts to hydrogen. Hydrogen's helium. But then you go to the next element, and stars basically cook up everything that you need to make us. You'll notice that the curve bends over at the top there. That's because when you get to nickel, it turns out that if you add more neutrons and protons, the nucleus is not stable anymore. Now, these are all things that Madame Wu mastered in her education to become an expert on nuclear physics. On the next slide, please. On the next side of that curve, however, there are more elements. In particular, the elements in blue there are needed to make you. That is, some of the atoms in your body are from the elements on the blue side of that curve. And we know they only are created when stars blow up in supernovae. So there's a very famous saying by Carl Sagan, at least made popular by Carl Sagan. He said, "You are made of star stuff." And it literally turns out to be true. There are parts of your body that came from stars, both from the initial cooking as well as the heavier elements from supernovae explosion. That's how intimately connected humanity is to nature. And to me, this is one of the most deepest truths and beautiful truths I know about science. Next slide, please. And so there are the two processes, cooking things up and thereby gluing them together when you go up the red side of the curve, and then stars having to explode to produce the heavier elements, including the nuclear elements that are naturally radioactive, which is the domain of Madame Wu's work. Next slide, please. So lots of people contributed. In fact, we've heard the name of some of them. One of them was Enrico Fermi, who actually gave a huge push in the 30s to our understanding why those curves have the shape that I showed you. Because remember, science is about observing nature. In fact, one thing I often talk to the public about is when people have questions about what is science, I say, science is really about what we are capable of observing and measuring. It's not about other things. And this turns out to be critical, especially for people of deeply spiritual beliefs, because this says science is about measurement, and that is what science is about. If you have a spiritual belief, can you measure it with an instrument? That's the challenge. And that acts, in fact, as a barrier between the two sets of belief systems coming into conflict with each other. Stephen Jay Gould, an evolutionary biologist, is a person who enunciated this most clearly when he talked about non-overlapping magisteria, that the two realms, in fact, do not collide with each other. And so that set of equations that you see there, we actually heard about in the last two lectures. That is, this is Fermi's first attempt to explain the forces that cause nuclei to fall apart, the natural radioactive force, the beta interaction. And so these mathematical expressions, which I'm sure those of you who are physicists in the audience appreciate, and those of you who are not physicists, maybe not so much. When I teach my students who are not physics majors and they see things like that, I say, don't get out the holy water. This is not going to hurt. Think of it like a musical score. No one's afraid of a musical score. So why should you be afraid of these symbols, right? So this is Fermi's contribution to so-called four Fermi interaction. And it was one of the first things that I studied as a graduate student at MIT, making my way into this profession. Next slide, please. And now, of course, we've heard a lot about these two young men. These, as Lars said, these two, he didn't say it, but we could have paraphrased what he says by these two rock stars in Sweden in 1957 for the great accomplishment of understanding the implications of parity non-conservation. Now, I've heard parity conservation today talk about, or non-conservation talk about it in terms of science or what have you. And just like the previous story when my technology failed me and I tried to explain to you where nuclei are, I'm going to try to leave you with a layman's understanding that will allow laypersons, people who are not scientists, to get exactly what Madame Wu was responsible for teaching us. Next slide, please. Two gentlemen who were working, even though they later became Nobel laureates, two people we actually heard mentioned in the talk just prior to mine about B-A. That was very much a discussion at Caltech by these two giants of physics, Richard Feynman and Murray Gell-Mann. And I have to tell you, I was fortunate enough to be a research postdoc in their group when in the 1980s. So I actually had interactions mostly with Feynman, but not so much with Murray because he was tending to a very ill wife. Next slide, please. So now we can enter the world of Madame Wu. I have set the stage for this story that I want you to have a takeaway from. So beta decay is very interesting because if you take a neutron and you take it outside of the nucleus of an atom, it will become a shapeshifter. What do I mean by that? Well, on average, if you wait just over 1,000 seconds and you could hold a neutron in your hand, after 1,000 seconds or so, what you would find is that the neutron is no longer there. Instead, it's a proton. And that's what I mean by it is a shapeshifter. We call this a radioactive decay, but in the language that you can talk to with your friends who are not scientists, they'll understand shapeshifter. And so because of charge conservation, it can't just turn into a proton. It has something else has to balance out the fact that the neutron has no electric charge. That something else is the electron. And then finally, because of some very careful studies by Pauli and people who were thinking about momentum conservation, we discovered that there had to be yet a third particle present. So when the neutron disappears, 3 particles replace it: proton, electron, actually electron, antineutron, and also neutrino. So what did Madame Wu teach us? Next slide, please. Next slide, please. Well, let me take you back even further in science, because back when Galileo was wondering about physics, the question was, what made the planets move? Now we know the answer today is, well, it's gravity. The planets orbit the sun, and it's the forces of gravity that keeps them in circular orbits. So this is a sort of a cartoon looking down from the North Pole of the solar system at the planets. And you'll notice they all rotate in the same direction. They're all rotating in a counterclockwise direction. Next slide, please. And if you look at our planet Earth from the North Pole, you will also note that it rotates in a counterclockwise direction. Now you can ask this question, and we have next slide, please. And I can see that our animations don't seem to be working, so I'm going to have to do this again by waving my hands very, very fast. So the Earth rotates in a counterclockwise direction. So I'm using my right hand to indicate that. And most of the planets, oh my goodness, it's working. Thank you, gentlemen. So here we see Earth, that is in fact Venus that we're seeing. You'll notice Venus is rotating in a counterclockwise direction. So now let's ask ourselves a thought experiment, something Albert Einstein was very famous for. Let's imagine that we were astronauts, and let's first say we're scientists. And so we do some experiments on Earth on how gravity works, and we basically learn what Newton told us, Newton's law of gravitation. Now, let's imagine in our imaginary spaceship that we can go to Venus and perform those same experiments to try to figure out, how does gravity work? Now, you would be surprised if I told you it worked differently, right? Your expectation is that gravity will not depend on whether you're looking on a planet where the Earth is rotating like the Earth, which is rotating counterclockwise, or on Venus, where it's rotating in a clockwise sense. But Madame Wu's experiment tells us something very interesting. There are 4 forces in nature, and the weak nuclear force, which is responsible for the beta decay. If you could imagine doing an experiment, you would find out if you lived on a planet that was described by an electron spinning in one direction, the nuclear force acts differently if you go to a planet where that's spinning in the opposite direction. And that's the magnitude of the unexpected nature of parity violation. It's that the law, one of the laws of the forces of nature depends on whether the body you're thinking about is rotating in a counterclockwise sense or a counterclockwise sense. Nothing else that we have ever discovered in physics looks like that. It is a singular observation about the structure of our world, that this one force depends on what direction spin is going in. This discovery has staggering implications. One of them is likely the source for why, as was alluded to earlier, we're here at all. Because you see, if there were equal amounts of matter and antimatter and all the forces were exactly the same, then all of the antimatter and the matter would have gotten together shortly after the Big Bang and produced a big fizzle. And we wouldn't be here. Thank you.
Wow. Jim, this is breathless what you have just said, explaining to people who may not know physics in such a beautiful manner. Thank you again. Okay, let's move on. The next we have is Professor Elena Apriali. I hope I pronounce it correctly. That's an Italian word, Apriali.
Aprile.
Apriali, sorry.
Yes, like the month of April. Within.
Okay.
Thank you.
And she is from Colombia. She, just like Madame Wu,
Oh.
actually, it's not just like Madame Wu was the first female faculty member in the physics department, and I was told that Elena is the second woman in the physics department, unless I misheard. Also, she also told me that Madame Wu often goes to her office and have chit chats with her, probably about beautiful science and physics and maybe something else as well. So it's so good to have Elena here today. Thank you. Go ahead.
Thank you so much. Yes. Indeed, it's a pleasure and a privilege to be standing here, honoring Professor Wu's legacy and contribution to modern particle physics. Her impact goes beyond the seminal and groundbreaking work that changed the direction of research in the field of weak interaction physics. And we have heard so much about it until now. As a woman in a field almost entirely dominated by men, when most doors were closed to women, she was a trailblazer with an indomitable spirit and determination and a focus on her scientific inquiry. How difficult it must have been for her at a time in history when societal expectations of women and the preconceived notions of women's role at home and in the world were so different. And what an irony that I myself joined this physics department of Columbia University in 1986, 41 years later than she did, to find myself again as the only woman in a faculty at that time, or more than 30 or so. It was a different world then, of course, a little bit more advanced than when she started, but it was still the task of the woman to prepare the dinner at home, even if she had a long experimental run in progress. And as we just heard, yes, Professor Wu would joke with me and tell me that my experiment would have to take priority over going home to my child and prepare dinner. You see, I was a young mother then of my first, young mother of a 2 years old, of course, married to a wonderful man, one of the greatest physicists I've known. But he was such a lousy cook. So, and I'm such a good Italian raised, nobody can cook as good as I can. So Carl would pick our daughter up, but it was up to me to be there and prepare dinner. And I always struggled to, not always be late. With no mentoring or support and no family other than my husband, it was challenging to balance my life at home with this relentless pressure and expectation of getting tenure at Columbia. Professor Wu was the only other woman professor before me in that famous department, which was heavily influenced by the presence of TD at the time. I still recall the lunch at this favorite Chinese restaurant on Broadway after I gave my interview talk at Columbia, which he openly appreciated. And I talked about detecting neutrinos, we just heard, neutrinos from the sun, neutrino from those supernova explosions, which makes us using the novel idea of a liquid argon imaging detector of unprecedented mass scale, of which I had worked on at Harvard as a postdoc in the group of another giant of physics, Professor Carlo Rubbia, who got the Nobel Prize in 1984 for the discovery of the W and Z bosons. I learned a lot about noble liquid detectors and a lot of other stuff from Rubbia. He also taught me, first as an undergraduate student at CERN under his supervision, and later as his postdoc at Harvard. He also taught me, with a lot of pain in many moments, how to be a strong and a better experimental physicist. But he did not prepare me, or nobody prepared me, to be the only woman in a physics department, or to face a classroom of hundreds of undergraduate students who expected the professor to be the male professor. So it was quite challenging to stand out there in the spring of 1986. I didn't dare to ask any time off, when you first got hired, and do all this negotiation. Nobody taught me that. You go straight and teach, and I find all these people and they look at me like I'm an alien, because they didn't have the expectation of the physics professor to be a female. In my early years at Columbia, I have to say TD was the one who gave me the most support through its kindness and interest in my work. I'm sure that I can only imagine how much harder it must have been, how much more difficult it must have been for Professor Wu at her time. She probably had to be even stronger. And indeed, when I first met her, her strength, it was intimidating, even to me, that I tried to survive the Rubbia effect, but she was, all these intimidating people, but then eventually you learn how to appreciate that she was so sweet, of course, inside. And I think you could feel that she had to fight at every step of her way to be, we heard about this today, to be recognized as the giant in physics that she was. But she was prepared. She was fighting all the time. And I kind of started to say, I don't want to fight you. I'm just here to learn from you. So she was already retired when I joined, and she was not too often on campus. However, when she would come to Pupin, she really liked to stop by my office to chat and to listen to me. I still can see her beautiful face with those white hair at the time already. and sitting on this chair that I treasure next to my desk, listening patiently about my problem at home. Yes, we would talk sometime about my daughter, but also mostly about the challenge and the stepping stones results that I would get from my early experiments using liquid argon. First liquid argon and other materials later. I used a variety of radioactive sources, including our favorite cobalt-60 to irradiate argon, then krypton, and later xenon. To measure, my goal was to measure as precisely as possible the response of this noble liquid to radiation. And so, and you know, when I told her about my idea at some point a few years later, encouraged by discussion with TD to propose a liquid xenon time projection chamber to search for neutrino-less double beta decay, using double beta decay of xenon 136. I still remember that CS Wu eyes lit up, and she started to open up and tell me about her love for xenon isotopes. And I had no idea that her PhD studies in Berkeley with Segre, this other great man that Italy has given us. I didn't know that. And so she started to tell me about her impact on the Manhattan Project. For me, it was just mesmerizing to know that her work on xenon 135 helped Fermi and others overcome the unexpected problem that they found with the first nuclear reactor that ever built. Fermi, we know that suspected that xenon 135 with its large neutron absorption cross-section was the reason for the problem, but it was up to CS Wu work to confirm it. That's, I find it quite tremendous. She remained interested in my experimental work until she passed away. I still remember the funeral in Manhattan that I attended. And I treasure every moment that I had with this wonderful woman and physicist, really. I find so many similarities. She had left her country, we heard, to pursue her studies and her dream in the United States and never went back. And my story is similar, although of course I was allowed to go back and see my mother and father, although it started 50 years later. To know that she married and had a son, Vincent, granddaughter, gave me strength that the choice I made to have it all was the right one. I wanted to have it all, and she was this great model. She did it all. But to know that she was so addicted to details and precision and was so strong that she strived to improve her experimental skills and results was even more encouraging and made me feel that my time in the lab was worth even at the cost of missing another of my daughter's birthday and not feeling guilty. Progress in physics is enabled by progress in the technologies and the tool that we need to make discoveries and test new ideas. I think it hasn't been said, but there were a couple of innovations or challenges that CS Wu and colleagues had to overcome to enable that experimental verification of parity violation. So the innovation to overcome those two major difficulties for her apparatus to enable this wonderful and legacy and result, it's a testament. It's a testament of this principle on which my own research career stands. It's only by optimizing the apparatus that we design to test an idea that we can reach more precise results and discovery. And John Lai here is doing the same. Yes, I think that it's something that I'm doing every day. It's my own quest to, I mean, it's really the innovation to overcome these difficulties that make us go ahead and achieve progress. In my own quest to answer one of the most fundamental questions we have open in cosmology and physics today, the nature of the dark matter that dominates the universe, I follow this path continuously improving this liquid xenon time projection chamber technology that we are using to search for the rare interaction of dark matter particles with xenon atoms, with perseverance, with dedication, of course, with the help of my collaborators, starting from my own graduate students and postdocs. We have managed to improve the sensitivity of our apparatus, of our experiments to search for dark matter by maybe over almost 5 orders of magnitude over the last 20 years since I started the project. And so my determination to realize the best experiment to answer the important question of dark matter is relentless. And for that, I have to thank my role models like Rubia, like T.D. Lee, like C.S. Wu. I stand on the shoulders of giants, and I know that progress is made in small steps, both in physics and in changing the environment to enable diversity in science. It is thanks to the effort of Professor Wu and other women scientists that we are able to break paradigms and change the status quo. Madame Wu is a member of a rare breed. She's the women physicist at the pinnacle of their profession. I mean, I'm honored, we are honored at Columbia to have such a role model. We are all honored to have such a role model. And I'm proud to have continued what she started at Columbia, becoming myself, I hope, a role model and supportive colleagues and friends for my younger women colleagues, and both at Columbia and worldwide. Thank you.
Thank you very much, Elena, for this mesmerizing talk. Next, we have Adrian Liu from University of Pennsylvania. Adrian has been very, very helpful to us in organizing this particular event. She is a world-class physicist, and the screen is yours, Adrian.
Thank you so much, Shin. I'm very honored to speak. So, well, as a theoretical statistical physicist working in the field of soft and living matter, I don't have a lot of scientific overlap with Professor Wu. But this celebration actually made me realize that she had a profound impact on my life that I hadn't fully recognized before. So I actually remember exactly when C.S. Wu first became my hero and where I was sitting at the dinner table at the time. I was 7 years old. So to tell this story, I need to go back a bit into my family history. My parents were born in China. They were young teenagers when they fled with their families to Taiwan in 1949. They both came to the US for graduate school, met here, got married, and stayed here. My mother, Annabelle Liu, or Liu Anhua, was a journalist and writer in both English and Chinese. And my father, Sam Liu, or Liu Shibe, was a theoretical condensed matter physicist. He was at IBM Yorktown when I was born, but soon joined the physics faculty at Iowa State University in Ames, Iowa. It's hard to describe what it was like to grow up as a Chinese girl in small town Iowa in the 1970s. Until my younger brother started school, I was the only non-white in my elementary school. And by the time my classmates had reached kindergarten, they had figured out that I was different. I wasn't bullied, but I was ostracized. No one would ever play with me during recess. I managed to pass kindergarten, but was so miserable at school that I nearly failed first grade. I had a lot of trouble learning how to read and struggled in the lowest math group. And that's when my mother intervened, telling me that while I would never be able to get my classmates to like me, I could make them respect me. Looking back, I think that my father was worried that I might take her message in the wrong way. So that night at dinner, he told us about C.S. Wu, how she came to the US from China and succeeded out of sheer talent and hard work. he described how she performed the groundbreaking experiment on parity violation, and that she should have gotten the Nobel Prize and didn't, probably because she was a woman. But what I remember is that he said that it didn't matter. She wasn't doing physics for the recognition, but because she loved it. And then he suggested that we should all want to learn as much as possible, not to show others up or for recognition and grades, but because it was fun. I have no idea of how much he said was based on what he actually knew about Professor Wu and how much he actually made up to convey a message to me. But this story and the advice stuck. I learned to truly love learning. And even though I'm no C.S. Wu, I do physics now because I love it. There's no question it's much easier now for Asian women in physics than in Professor Wu's day. There are a lot more women now and less bias compared to when I was a graduate student. But things are not nearly as close to equal as many of us would like to see. When my hair turned gray, quite quickly in my mid-30s, I transformed within a year in my teaching evaluations from a sweet young thing who didn't know what I was teaching, okay, to a dragon lady who knew my stuff but was really nasty. Women still face more resistance and obstacles than men, and anti-Asian prejudice sometimes seems stronger than ever in this country. It's up to all of us to always try to recognize and fight back against bias in all its forms. It's also up to us to ensure that Chinese students and scientists can feel as welcome to come here and do great work as Professor Wu did, or more welcome, really. To do that, we have powerful stories like Professor Wu's that inspire and guide us, and that we can pass on to others. I hope that broader recognition in the form of the postal stamp and this important occasion today will help her amazing story spread well beyond physics. All of us can use the reminder that when we pursue something that we love, we can let the recognition and the approval of those around us, or the lack of it, fade away as we just focus on the hard work of having fun. Thank you.
Thank you very much, Professor Liu, for this heartwarming talk.